Okay. So today we're going to be diving into something pretty mind-blowing, something that could, well, it could really change the world as we know it.
Oh, yeah, definitely a game changer.
Yeah. We're talking about quantum computing, but not just any quantum computing. This is about a potentially massive breakthrough from Microsoft. They're calling it Majorana One.
Mm-hmm.
And what we have here is some really interesting info about it, so we're going to break it all down for you. No jargon, just the core insights of what this all means.
It is a pretty dense topic, so yeah, we'll try to cut through the noise, so to speak.
Exactly. So, like, why are we even chasing this quantum computing dream, right? What's the big deal?
Think about it like this. Our regular computers, powerful as they are, kind of hit a wall when it comes to certain problems.
Okay, like what kind of problems?
Well, imagine trying to simulate, let's say, the behavior of just a small group of electrons, like 30 or 40.
Okay, small.
Sounds simple enough. But the calculations involved explode exponentially. It gets so complex that even the most powerful supercomputers we have today, they would literally take longer than the entire age of the universe to solve it.
Whoa. So it's like a time barrier, basically.
Yeah, you could say that. Classical computers just can't handle that level of complexity when it comes to modeling the quantum world. And that's a huge roadblock in so many fields like medicine, material science.
It's like trying to fit an ocean into a teacup.
Right. So that's where quantum computers come in. They work in a fundamentally different way. And their potential, that's off the charts.
And that difference boils down to the qubit, right? The quantum bit. I mean, everyone knows computers use bits, ones, and zeros, on or off states. But qubits are a whole different ballgame.
Yeah, they can be in a superposition.
Which is,
It's like being in multiple states at the same time. Imagine a light switch that's both on and off simultaneously. It's mind-bending, but that's quantum for you.
So it's this both at once thing that gives them that crazy parallel processing power, right? Like doing millions of calculations at the same time.
Exactly. But there's a catch, and a big one. Qubits are super fragile. They're extremely sensitive to any kind of disturbance, any noise from the environment.
So any little hiccup throws off the whole calculation.
Pretty much. It's like trying to build a house of cards in a hurricane.
Oh, that's a good one. So this instability, it's been the biggest hurdle in making quantum computers actually useful, right?
Absolutely. It's the challenge that researchers have been wrestling with for years.
And from what we're seeing, it sounds like there's always been this trade-off with qubits. Like, you can get stability, but then you sacrifice speed or size, or vice versa.
You got it. It's been a real balancing act.
So it's like trying to juggle chainsaws while riding a unicycle.
Uh-huh. Yeah. Something like that. It's really tough to find that sweet spot where you have qubits that are stable, small enough for practical devices, and fast enough for real-world computations.
So where does Microsoft's Majorana One fit into all of this? It sounds like they're trying something completely different.
They are. It's like they looked at all the existing qubit technologies and said, you know what, let's just throw all that out and start from scratch.
A clean slate.
Exactly.
Yeah.
Think back to the early days of computers, like with those giant vacuum tubes.
Oh, yeah, I've seen pictures. Huge things.
They worked, but they were bulky, inefficient, and unreliable. And then came the transistor. That was a true game changer.
Much smaller, more efficient, way more reliable.
Right. And it seems like Microsoft is trying to pull off a similar revolution with Majorana One.
So they're not just tweaking things here and there. They're going for a fundamental shift, a whole new type of material, a whole new way of building a quantum processor.
Yeah, they're aiming to bake error protection right into the core of the system.
That's incredible. And the way they're doing it, it's almost like science fiction.
Well, it does involve some pretty exotic physics.
Okay, so we're talking about topological states of matter, right?
You got it. Now, we all know about the regular states of matter. Solid, liquid, gas. They're defined by how atoms behave.
Right. Ice melts into water, water boils into steam, basic stuff.
Exactly. But about 100 years ago, mathematicians predicted that there could be these other, more exotic states of matter called topological states.
Okay, and these are different how?
Think of it like a pretzel.
A pretzel.
Yeah, bear with me. You can twist and bend a pretzel into all sorts of shapes, right?
Yeah.
But the number of holes it has, that stays the same unless you tear it apart.
Okay, I'm starting to see where you're going with this.
Topological states are kind of like that. They have these inherent properties that are incredibly robust, immune to certain types of disturbances. They're like those pretzels. Their essential structure stays the same even when you mess with them.
So Microsoft is using these weird topological states to build their quantum computer. How does that even work?
It all comes down to this special quasi-particle that exists within these topological states. It's called a Majorana particle.
Okay, a Majorana particle. Is that even a real thing?
It's been theoretical for a long time, but the exciting thing is that the info we have suggests they've not only observed it, but they can actually control it.
So they're not just messing around with theory, they've got their hands on the real deal.
Yeah. And that's the real breakthrough. This ability to manipulate Majorana particles is what allows them to build what they're calling a topological qubit.
Okay, but what's so special about these Majorana particles? I mean, why are they the key to all of this?
Well, to put it simply, a Majorana particle is its own antiparticle.
Wait, its own what? That doesn't even make sense.
I know, it's one of those quantum things that kind of melt your brain a little.
Yeah.
But think about it like this. When two Majorana particles meet, they can either completely annihilate each other.
Like matter and antimatter colliding, poof, gone.
Exactly. That would be like the zero state, nothing left. Or they can remain as two distinct particles.
Okay, and that would be like the one state, right? Like an electron.
You got it. So you have this strange duality built right into the particle itself. It can be both nothing and something at the same time.
That's wild. So how does that make a qubit?
Well, it's this weird self-identity property that makes Majorana particles perfect for building these super-stable qubits.
Hmm.
By controlling them, they can encode and manipulate quantum information in a way that's naturally protected from that pesky environmental noise we talked about earlier.
So it's like the information is encoded in the very fabric of the topological state itself.
Exactly. It's not stored in a single fragile point. That makes it way more resilient to any kind of local disturbance.
It's like writing a message on a beach. A wave might wash away part of it, but the overall message is still there.
That's a great analogy, and that's the beauty of topological qubits. They're inherently more stable. They have the potential to be much smaller than other types of qubits, and they can be controlled really effectively.
So they're ticking all the boxes: stability, size, and controllability. This is starting to sound like the holy grail of quantum computing.
It's definitely a huge step in that direction.
All right, so let's talk about the Majorana One itself. This is the actual quantum processor that Microsoft has built using this crazy topological architecture, which they call the topological core.
Right, and one of the most mind-blowing things about it is its potential for scalability.
Mm-hmm.
We're not talking about just a few more qubits. We're talking about potentially going from tens or hundreds of qubits to millions.
Millions on
Yeah.
a single chip.
Yeah. And not just any chip. A chip small enough to fit in the palm of your hand.
That's insane. I mean, current quantum computers, they're these massive machines, right? Like room size.
Yeah, and that's just to accommodate a relatively small number of qubits. And even then, they're super sensitive to noise.
So to have a million stable qubits on something so tiny, that's a complete game changer.
It is. It's like going from a horse and buggy to a spaceship.
And from what we're seeing, it sounds like they're building this thing from the ground up, literally atom by atom. Every atom in this chip is placed with a specific purpose.
Yeah, it's like they're painting a picture, but instead of paint, they're using atoms.
It's mind-boggling, the level of precision involved.
Oh, absolutely.
Yeah.
And another important thing to understand is that the Majorana One doesn't use electrons for computation like our regular computers do. It's using those Majorana particles themselves.
So it's not just a new architecture, it's a whole new type of computing based on a whole new particle.
Yeah, it's really something else. It's like discovering a new element and immediately figuring out how to build a supercomputer out of it.
Okay, so just to recap the major advantages here, we have this incredibly small form factor, the potential to pack over 1 million qubits onto a tiny chip.
Right. Plus, it's got the potential to absolutely crush those super complex calculations that would take classical computers forever. And don't forget, it all comes down to that topological qubit design. The right size, the right speed, and the right controllability. That's what makes it so scalable.
So how would something like this actually work in the real world? I mean, it's not like we're going to be carrying around quantum computers in our pockets anytime soon.
Well, probably not anytime soon. But the way it's envisioned is that the Majorana One would work as a kind of quantum accelerator. You'll be part of a hybrid system where it teams up with a classical computer.
So it's not about replacing our existing computers, it's more like augmenting them, right?
Exactly. The classical computer would handle the overall control and feed the Majorana One those really tough problems that are perfect for quantum algorithms. Then the Majorana One crunches the numbers at lightning speed, and the classical computer takes those results and makes sense of them for the user.
So what kind of problems are we talking about, though? What are the potential applications for something like this?
Oh, man, the possibilities are huge. I mean, imagine being able to accurately simulate the laws of nature at the most fundamental level. That opens the door to breakthroughs in pretty much every field you can think of.
Like what specifically?
Well, medicine is a big one. We could design entirely new drugs, ones that target diseases with incredible precision.
Like personalized medicine on a whole new level.
Exactly. And material science is another area where this could be revolutionary. We could literally design materials from the atomic level up with specific properties that we want.
So instead of spending years in the lab, mixing and testing different combinations, you could just design the perfect material on a computer.
Right. It's like, imagine a scientist says, I need a material that's super strong, but also incredibly lightweight and flexible, and boom, the computer spits out the exact blueprint. First time, right?
So no more trial and error, just computational design.
And think about the implications for energy storage. We could design batteries that are way more efficient, maybe even batteries that never discharge.
Now that would be a game changer.
Oh, yeah. And there's this whole other area that gets really exciting when you combine quantum computing with AI.
Yeah, AI is already exploding, but quantum computing could take it to a whole other level.
Totally. I mean, quantum computers could give AI the raw processing power it needs to solve problems that are currently impossible. We could see huge leaps in machine learning, maybe even the development of entirely new forms of AI.
So we're talking about AI that can design new chemicals, new drugs, maybe even new enzymes that could revolutionize food production.
It's all on the table. And the crazy thing is, we're probably just scratching the surface of what's possible.
It really feels like we're on the cusp of a new era. The information we have even makes this comparison to how different materials have defined different ages of humankind.
Yeah, like the Stone Age, the Bronze Age, the Iron Age.
Right. And now we're in the Silicon Age. But what comes next? What happens when we can manipulate matter at the atomic level?
It's a pretty profound question. And it's not like this happened overnight either. This research has been going on at Microsoft for something like 17 years.
Wow, 17 years. That's dedication.
It is, but it just goes to show you the scale of this challenge. This is cutting-edge science, pushing the boundaries of what we know about the universe.
And now, after all that time, they're finally showing us what they've achieved with the Majorana One. And they're saying these are real results, not just theoretical.
It's a huge deal. It really feels like the dawn of a quantum age.
It does. So the key takeaway for you is this. The development of the Majorana One and its topological qubit architecture, this is a potential game changer. We're talking about stable, controllable, and massively scalable quantum computers. The kind of technology that could change everything.
Exactly. I mean, think about what it means to be able to accurately model nature at its most fundamental level. That's the power we're talking about here.
It's almost overwhelming to think about the possibilities, and that's what we want to leave you with today. Imagine a world where we can design materials and molecules at will. How would that change our technology, our relationship with the physical world? It's a pretty amazing thing to ponder.
Definitely something to think about. It's not just about faster computers, it's about a whole new way of interacting with the universe.
And on that note, thanks for joining us on this deep dive into the world of quantum computing. It's a journey that's just getting started.
Absolutely. Who knows what the future holds, but it's definitely going to be exciting.
That's for sure. Until next time.